Good.
All right, so we are ready. Sorry for the hiccups. All right, so I'm going to talk a little bit about a polarimeter antenna. Some of us are using this type of antenna, and I think you saw some of the plots there using this antenna. So I'm going to talk a little bit about this antenna and probably end up with something like a challenge for using the Jupiter polarized emission. So the emission from Jupiter is either circular or elliptically polarized. And so the different sources of emission are emitted either in the right circular or left circularly polarized. And that depends on the sources, which I'm going to show you a little bit in a few more slides. So the emission mechanism is called the cyclotron maser instability. And the frequency at which it's emitting the emission from Jupiter is pretty much in the formula there, in which the frequency is equal to about 2.8 times B, with the frequency in megahertz and B in Gauss. According to all the models, the emission is emitted in the X mode of the cyclotron maser. There is an O mode, ordinary mode, but it seems that the intensity is too low, so that normally the X or extraordinary mode is the one that is being considered for doing that. And the other important thing is that the emission is completely polarized, either right hand or left hand, circular or elliptical. And the polarization of the emission depends on the sources there. The sources located in the north hemisphere are predicted, according to the model, to be right-hand polarized. And the sources in the southern hemisphere, the polarization is pretty much left-hand polarized. So in order to receive the maximum power of the emitted wave, one had to use polarized antennas, in that case, either right-hand or left-hand polarized antennas. So there is a match between the antenna and the polarization of the wave. Here I have a plot by Dave Tepinski characterizing some of the polarization and the structure of the emission that you receive from different sources. So on the left side here, you can see that emission from the north hemisphere are right-hand polarized, and that includes the sources IOB and IOA. And the sources in the southern hemisphere are left-hand polarized, and that include the sources IOC and IOD. I didn't include the non-IO related sources, but these are the main sources related to the position of Jupiter. So in order to receive the maximum of emission, you have to use antennas that can receive either the right hand or the left hand or both of them. So you receive the maximum power from the emission. Of course, a linearly polarized antenna will receive the emission, but because of the mismatch of polarization between the emission and the antenna, you don't capture the full power of the wave, but you can detect the emission. There is no problem. And the other important thing is that using one dipole, yeah, you can detect the emission, especially from the sun, which is very powerful, and in some of the powerful Jupiter's emission also. And the two dipole array is the standard for the radio JOVE, there's no problem. They can detect the emission, and that is pretty much what is being sold right now as part of the kit for the radio JOVE. So here I have a sketch of the 4 elements, and the 4 elements are in a square, and these are TFD, terminated folded dipoles, which are some kind of antenna that Dave Tepinski actually implemented, and I'm using that in an antenna that I have in Rosemary Hill near Bronson here in Florida, and many people are using this type of antenna. So you can see there that the dipoles located north and south, the power come together with the power combiner, the east and west in another power combiner. And you can see also, see if I can show you here, that there is 2 cables there, A and B. Those cables are used to point the antenna south in the direction of Jupiter, if you are located in the north hemisphere. Those are the facing cables that are described in the manual there. And then finally, you take the emission from the north and south antennas, and you combine there in the 90-degree hybrid, and from there you finally separate the right hand and the left hand, which you send the signal there to spectrograph if you're using a right hand and left hand spectrograph. Right here, and many people are using an old spectrograph, which is called the FSX7, but some of the people who are using the new radio JOVE normally receive only 1 polarization, but the other polarization can be available if you're using this type of things here. So here, just to be more specifically, you have a right-hand wave, which is being received by the square array, and we're using here the IEEE convention for doing that. Here we have another one. These are just regular dipoles, similar to what is being sold right now as part of the radio JOVE 2.1 at about 2.1 megahertz. They are much narrower in bandwidth than the TFD, but you can put them in a square also, and you can combine in the same way with 2 power combiners here, and from there you can go also to a 90 degrees hybrid to combine the things. Here I'm showing pretty much what I have here at home in my small observatory here, and the one that was using Wes Greenman. By the way, Wes Greenman passed away a couple of years ago. He was one of the original members of the radio JOVE, and he used here a ring made of coaxial cable, RG59, and here you can see the coaxial cable, and there is another addition here, and then you can separate the right and left emission also. I'm using these kind of things, a hybrid ring made of coaxial cable, RG59, and also for combining the power, I'm not using here a power combiner, the wideband. I'm using actually a hybrid ring to combine these things. So here is one example from Tom Ashcraft in New Mexico. He's using the terminated folded dipoles in a square configuration, so he can get the right hand and left hand. So here is an emission from the IOD source, and you can see that the emission is much intense in the right hand than in the left hand, but you can see a little bit in the left hand also. The big advantage here is that he has a wider bandwidth using the TDF component. Here you have another one. This is a record that I made here at home near here in Gainesville, Florida. And I'm using 4 dipoles in a polarimeter array at 20.1. And you can see here part of what is called the N event or N emission, narrow band emission here, which is right hand, and you cannot see almost nothing in the left hand. All right. Another example here, taken from an observation in Rosemary Hill Observatory, one of the observatories of the University of Florida. And I have there a TDF array. It's a polarimeter array. And you can see that here we have emission from the IOC source, which is left-hand polarized here. All right. So one of the questions is that, yeah, you can detect the emission and tell which source you are receiving the emission from. So the source is normally emitted so that you can identify the circular polarization, right hand or left hand, and from there you can actually detect the source. And also using the shape of the arcs that produce the emission, they are called vertex early or vertex late. You can identify the emission. And the other way to identify the emission coming from a given source is by using the location when you are receiving the emission in the CML and IO phase diagram, which is something that Dave Tepinski was showing there. So in that way, according to the models and according to what we have been observing for many years, you can identify the emission. Now, an interesting question, is there a direct observational evidence to identify the location of the hemisphere where the sources are? And that is still in the making. We don't know exactly where to do that. And here I'll show you some of the things that we have been doing. Some of the problems here are that in order to detect the emission coming from either the north or south hemisphere, it's kind of problematic at low frequencies. For example, in the case of the Earth and how separated we can see the sources there looking from the Earth, and the size of the beam of the low frequency antenna is one of the problems. So, and the other part of the problem is the changing structure of the terrestrial ionosphere, which is changing in all levels, including a few kilometers or so. You can see that the propagating through the ionosphere depends on the location there. Just to give you an idea, near Jupiter emission, the separation between the north and south sources is in the order of about 50, no more than 55 arc seconds or so. Well, the size of the low frequency antennas, the half power beam width is in the range of 40 to 60 degrees. So there is no way that we can tell from the size of the beam from where the source is emitting, either the north or south hemisphere. Even with big array, like 26.3 mega array that we have here at the University of Florida, which has 640 dipoles at 26 megahertz, or the French TP array, the half power beamwidth is a few degrees. So you cannot even tell from which hemisphere you are receiving the emission. So we attempted something here many years ago. It was probably a little bit more than 20 years at the University of Florida using an 18 megahertz interferometer. The project was led by Tom Carr. He was the PI, and part of the team was Kazumasa Imai from Japan, Wes Greenman, and myself. So one station was located at the University of Florida Radio Observatory near Old Town, and the other station pretty much north of Old Town in Live Oak in Florida. So the separation provided by the distance for the interferometer was enough to be able to have the source in one of the beams of the interferometer. So let me show you here a little bit more details. Considering that the separation in the north or south source can be in the range of 50 arc seconds, and if you consider the distance, the north-south distance between Old Town and Live Oak to be about 81 kilometers or so, the beam width between first nulls, or what is called the fringe separation, is about 42 arc seconds. So it's barely enough to have either the north or south source within one of the beams there. I give you the formula there to calculate the beam separation between the first null, in which you can calculate that in degrees, and the distance, in this case, between Old Town and Live Oak is in wavelengths at 18 megahertz. So you have to receive a mixture of right-hand and left-hand polarization, and that emission has to be received in a very short time, if possible, within a few minutes or even a few seconds, to avoid any changes in the propagation through the terrestrial ionosphere at each one of the stations. In a very short time you need that. So after a few years of using interferometer, we detected many storms, but we didn't detect any storm in which the right and left hand polarization were received at the same time, except for one occasion in which we detected the right hand emission from the short burst and the left hand emission from the long burst. The problem was that even with having received the emission leaked from the right hand to the left hand, especially with the L bursts, which were almost continuously being emitted during the time in which the S-bursts were emitting. So that didn't allow to separate the fringes from the two polarizations. We did a lot of changes there, but finally, according to Tom Carr, it wasn't clear that we were able to separate the emission from the two and be able to actually detect the emission from one or the other hemisphere. So here we have another example in which you can receive the right hand and left hand emission. This spectrogram is taken from the low wavelength array in New Mexico, in which you can see that the red color is the right hand and the left color, the blue color is the left hand emission, and it happened almost simultaneously. The problem here is that this was detected only with a single array, so it didn't have enough resolution in order to separate from which hemisphere the emission was coming. All right, so a final comment here is that, yeah, the project here is beyond the capabilities of the radio JOVE 2.1 because it requires the detection and recording of the emission to be processed offline, and you need actually the baseband of the receiver or the down conversion of the baseband and coordinating the time on both stations. So it's beyond what we are doing with the radio JOVE 2.1 there. So this project can be implemented as an extension of the citizen science band. It can be citizen science radio JOVE or any citizen science project there, but it requires a lot of complications there. And one of the main problems is that, yeah, it requires to meet several conditions, which are hard to meet in that case. One of them is regarding receiving the polarization, the right hand and left hand, in a very short period of time, and hopefully the behavior of the terrestrial ionosphere is nice so that you can do the same there. So using an interferometer is one of the possibilities, but there might be another different technique to do that kind of project. So this is still a project that can go ahead and done, but it will be interesting to actually detect the emission separated from the north and south hemisphere, which we know just from the projects and the emission from the models. All right, thank you very much. And if you have any questions, maybe I can answer some questions.
Thank you, Francisco. Any questions in the room? Yeah, Les.
I've got two questions. With respect to the interferometry possibility, what is the precision of the time tagging that would be needed to make that work over the baseband or the separation that you were trying?
Right. I can tell you what we try to do here. So we have two timings in both stations there. We brought together the two timers, and we were pretty close there from the frequency of the timing system, pretty close. But finally, when you digitize the emission, you can change a little bit the delay of the emission because you have to account for one emission being received a little bit earlier. Let's say in the case of Old Town, and a little bit later the case of the farther north. So you have to change a little bit the emission there and combine the data using like a simple interferometer there. So we recorded also part of the things. I think we recorded something like we were recording the DAT tapes, which are obsolete right now, at the maximum frequency. I think it was something like 20 kilohertz or so. And using that, like I said, we try to do our best in order to combine both of these things.
So you don't actually know in terms of actual time how close you need to be?
If I may add on timing, most of the JOVE stations and observatories have at least a few millisecond GPS clocks, and so we're within a few milliseconds of one another. Here myself, I have one that is actually within a few microseconds, which is more than enough for any science that we would do in radio JOVE.
Sorry.
Time tagging would be sufficient.
Yeah, so what Larry was saying, yes, that's right. Right now, you can use the GPS and have very good timing on both stations there. And so normally the bandwidth of the baseband that we use there was in the range of 15 to 20 kilohertz or so. So with timing within a few microseconds, you have well enough in order to combine the emission.
Thank you. Second question. Can you bring back up the image, any of them, of the 4 dipole arrangements?
What was that?
Can you bring back up the slide, the page that shows the diagram of the 4 dipoles being interconnected? Yes.
That one?
That
Yeah.
will do. Right. What is the purpose of the delay line after the combining network for the 2 dipoles?
Which one? This one here?
No, higher,
Or
right there. That. What is the purpose of that delay line?
the A and B, for example, in the case of the, if you are observing here, you have the upper part is the north, the south part is the south. So Jupiter is probably south of the zenith there. So the south dipole, the wave will hit the south dipole first, and the north dipole after that. So you need to add a delay here in the 8 facing cables in order to for the north and south dipole to be faced in the same direction as Jupiter. And
yes, I understand that, and I accept your explanation. Now, what is the explanation for the placement of the delay line on the other side?
oh yeah, all right. So here you have the north and south. So this cable here is twice this other cable, because this other cable there, the center of the dipole is somewhere in between the north and south. So you have to delay this emission there compared with the delay of the north-south also. So you have to combine the thing here in a way. You don't combine the thing directly between the east and west, but you have to delay the combination there in order to combine with the north and south dipole.
I understand now.
Thank you, Francisco.
All right.
All right, thank you, Francisco.
Yeah, thank you.
Quick logistics,